Hello and welcome to Open Logic. In this video, we're going to look at how bipolar junction transistor BJT works. And starting from an intrinsic semiconductor, we can divide it into three regions. The middle region can be doped with P-type semiconductor and the two sides are doped with N-type semiconductor. And this is an NPN transistor. Similarly, we can also dope the middle region with an N-type semiconductor and the two sides with P-type semiconductor, and this is a PNP transistor. From now onwards, I'll be focusing on the NPN transistor because every description is equally applicable to the PNP transistor. The difference between the two are the charge carrier type, the polarity, and the flow direction. Now, looking at the diagram, there are two PN junctions. One is here and another one is here. The two PN junctions are facing opposite direction and hence the name bipolar junction transistor. To operate on the transistor, we apply a voltage across it. And this is where a lot of people may get confused. The two PN junctions, we know that one of them is in reversed bias, and in that sense, current should not be able to flow through this semiconductor. Of course, this diagram as of now is incomplete. There is a dirt voltage which is applied at the middle region. Now, technically, we can apply a very high voltage so that the two junctions are forward biased, or we can apply a very low voltage so that the two junctions are reversed biased. But as far as I can tell, these two are not valid use case. The practical usage of the transistor is where we apply the middle voltage that can be as high as the high voltage here or as low as the low voltage here. To ease our discussion, let's say we apply a voltage that is exactly at the middle between the two voltages. Looking at this configuration, we know that this PN junction is forward bias and this PN junction is reversed bias. And to recap on reversed bias, we apply positive voltage at the N region and negative voltage at the P region. And to understand the behavior better, we should always include the electrons which are bounded by covalent bond. In reversed bias, the free moving electrons, which are the red electrons, are pulled towards the positive terminal and the electron holes are pulled towards the negative terminal. The white electrons, which are bounded by covalent bond, they can no longer move further because there are no electron holes in the N region. And generally, this is how reversed bias blocks current flow. On the other hand, this PN junction, which is in forward bias, we apply a positive voltage at the P region and a negative voltage at the N region. In this case, the electron holes and the red electrons move towards each other and cross paths at the middle. And this is where the red electrons will combine with the electron holes and become white electrons. In the P region, the white electrons can move towards the positive terminal because there are electron holes there. And this is how current flows through the PN junction in forward bias. And now let's look at the two PN junctions together. At the reversed bias junction, the red electrons are pulled towards the high voltage, and the electron holes are pulled towards the low voltage. The interesting part is actually at the forward bias junction. Intuitively, we thought that the red electrons will move up and combine with the electron holes and become white electrons. As white electrons, they continue to move up until a point where there are no electron holes to move on to. However, the white electrons can exit through this terminal, and by doing so, they leave behind some electron holes. Now, this thinking is not wrong, because we see the two PN junctions as separate and they don't work together. Now let's try to see how it really works. Imagine that when the red electrons cross over, some of them may not combine with any electron hole. If the red electrons remain free, they will be able to move across the reversed bias junction. The question is then, how would the red electrons escape combining with the electron holes? And this is where the design of the transistor gets interesting. First, we can narrow the middle region. This reduces the travel distance of the red electrons and also the probability of them combining with electron holes. Second, we can make the middle region lightly doped, and therefore there would be fewer electron holes there. And third, we can make this N region more heavily doped so that there are more free moving electrons. As a result, more red electrons cross over to the middle region, and only a few of them would combine with the electron holes there. As free moving electrons, they are attracted to the high voltage and they will cross the reversed bias junction. For those which are combined with the electron holes and become white electrons, they cannot move across the reversed bias junction, and so they will exit through the terminal here. And there you go. This is how free moving electrons cross this forward bias junction and then this reversed bias junction. And to emphasize again, the reversed bias junction here stops the white electrons from moving because there are no electron holes on this end region, but it doesn't stop the red electrons from crossing over. One thing to note here, this operation is only possible when this junction is in forward bias. If the voltage applied here cannot sufficiently put this junction into forward bias, then the red electrons cannot cross over, and subsequently there will be no current flowing through this reversed bias junction. In short, by controlling the voltage at this terminal, we can control the current flowing through this transistor. If we look at the PNP transistor, the operation is pretty much the same. First, the middle region is made narrower, and it is more lightly doped, whereas the forward bias region is more heavily doped. At this region where it is in reversed bias, the electron holes are being pulled towards the negative terminal and the white electrons are being pulled towards the positive terminal. Supposedly, the white electrons cannot move any further because there are no electron holes on this region. But because of the forward bias junction here, the electron holes are moving towards the middle region. Some of them will combine with the red electrons, but a lot of them will remain as electron holes. And now, because of these electron holes, the white electrons can move up. And so, in a similar manner, by controlling the voltage at this middle terminal, we can control the current flowing through the PNP transistor. Now that we've understood the operation, let's talk about some terminology. The middle region here is known as base, whereas this region in forward bias is known as emitter, and the region in reversed bias is known as collector. Now think of it this way, the emitter is responsible for providing charge carriers, whereas the collector is to collect them. For the NPN transistor, the emitter provides free moving electrons, and for the PNP transistor, the emitter provides electron holes. And these are the symbols for the NPN transistor and the PNP transistor. They look pretty much the same, and the way to differentiate them is by looking at the arrow here. The arrow here represents the direction of the forward bias junction, which is from base to emitter. If it is facing out, then this is an NPN transistor, or if it is facing in, then this is a PNP transistor. And now to reiterate, in order for current to pass through the transistor, the base emitter junction must be in forward bias. For NPN transistor, the base terminal has to be at a relatively high voltage, whereas for the PNP transistor, the base has to be at a relatively low voltage. In another word, an NPN transistor is turned on by a high base voltage, and the PNP transistor is turned on by a low base voltage. Application-wise, transistor provide the mechanism to control current flow electrically, and this allows a lot of automation. For example, an air conditioner can use temperature sensor to operate. When temperature is high, sensor can send a high voltage, and this in turn switches on the air conditioner. Or when the temperature is low, the sensor can send a low voltage, and this turns off the air conditioner. Another example is a light sensor and lamp. During daylight, the light sensor can send a high voltage, and this turns off the lamp. And during night time, the light sensor can send a low voltage, and this turns on the lamp. Alright, that's it for this time around. Please support by clicking like, share and subscribe.